Hello and welcome to the third and final session of the Sports Aerodynamics Workshop by SimScale. My name is Milad and I'm very glad to see so many people who have joined for our last session. Today we will finish our journey through the world of sports aerodynamics and talk about the influence of aerodynamics regarding the performance of a soccer ball. Before we actually start start with our presentation today, I would like to make sure that everybody can hear me loud and clearly. So guys, you know the game. In the case you can hear me, please click the raise your hand button to show me that everything is working fine. Great, I already see some hands. Perfect, seems like everything is working. However, in the case the audio stream should drop for you during this webinar, you can also use our toll-free audio service numbers to access the webinar. Therefore, just call one of these numbers and enter, once you're asked, the access code 722-525-973. Great. Then let's get started. As I mentioned, today we will talk about soccer ball aerodynamics. And let's take a quick look at our agenda. So first of all, we'll give you a very crisp and quick introduction to the workshop, just talk about some things which are important since this is the last session and a lot of you want to get certified. Just after that, you will get introduced to some fundamental models which can describe aerodynamics of the soccer ball. So we will talk about flow around the sphere and the influence of let's say, the size of the ball, the free stream velocity, etc. And after that, we have prepared again a nice live demo for you where we will investigate and compare two different very famous football designs. And finally, I will present your homework to you and we will have time for a Q&A session. Right, since this is the last session, just let's make some things clear because I again received a lot of questions. So mainly about the certification. So in the case you want to get certified, you need to submit all the homework to the submission deadline. The last submission deadline for the last homework ended last week, and today 12 p.m. the submission deadline for the second homework will end. In the case you may struggle with the time because you have some other things to do, you can also reach out to me and we will find a solution. Maybe we can extend your submission deadline if there is a good reason. And just because a lot of people are also sending me emails regarding technical problems, please use our forum, guys. In the case you are struggling with something, just write into our SimScale forum. You will find a link to the dedicated topic on simscale.com/sports, and if you have a problem you will get help there very quickly. And the good thing is that you can also discuss with other participants of this workshop. Great. And I also received a lot of emails from people who asked me, can I also simulate maybe not a bike but a bob and other questions. And if you're interested to learn about topics which are not covered here, I strongly recommend, first of all, to check out our SimScale public project library. You will find a lot of projects there which also relate to sports. Okay, but then let's get started. And as you know, today we will talk about soccer ball aerodynamics. And since this is our final session and you already learned some stuff about aerodynamics, you may already hear some things. But today we will talk about a lot of aspects more in detail. And let's first of all start with the basis definition. So, I mean, we are talking about soccer ball, also called football in UK or in Germany. And let's take a look at such a ball. First of all, you should know that the diameter and a lot of other things of these balls are defined by the international FIFA regulations. So there are, for example, the diameter must be in between a defined range, the same for the weight. One thing which it's where the manufacturers and developer of the sport devices can play is the structure of the ball itself. As you can see, this is a kind of classic old-fashioned football where you have this shaped patches which are stitched. And let's say our ball is flying in this direction, so it comes out of the screen. Then we have, first of all, three forces, and this is very similar to the ski jump. In the end, the trajectory of this ball is described by its forces. And first of all, we have the weight, which is the weight force, which we can calculate by multiplying the weight with the gravitation g. And this one here, it is constant. This is very important. This is constant. Oh, sorry guys, And then we have drag here, lift, and side forces. And maybe because to make this clear, since this is a round ball, basically we cannot really say what is lift and what's the side force. It depends on our coordinate system. But let's first of all stick on that, and later we will talk about this more in detail. And now let's take first of all a deeper look at the forces, the aerodynamic forces, which are colored in blue. And here we see, sorry, the forces are all colored in blue, which I will color them for you. Just give me a second. In green. So these are our aerodynamic forces. And special thing about these forces is they are basically a combination of two components. We have a viscous and a pressure component. You may remember we also talked about it during the ski jumper session. And as long as a smooth ball has no spinning, we have only drag, and all components like lift and side, since it's a symmetrical case, will not appear. But as soon as I'm adding a rotation to the ball, I will also get this lift and side forces. Well, and then let's continue. And take a little bit more about the aerodynamics of such a ball. As you see, we can simplify this ball with a sphere. Basically, it's a sphere. And as you remember when we talked about some basic fundamentals of aerodynamics like boundary layer and stuff like that, you can see it here applied on a sphere. And in theory, what we would think that we have here is a flow. We can see it here. Just use my laser pointer. So here we have the flow coming from the left, following the curvature of the sphere, and then somehow we have a wake. Region. Yes, and looks very beautiful. And in theory, this can happen, but only in theory. And he would have a quite low drag. But in reality, flow is looking different. And in reality, if you take a look at the flow around a football, or let's say sphere with the size of a football, you will see that we have a different kind of structure. And it's very important to know that the forces, and in the end, on the sphere are depending on the state of flow. And you can see this difference between the theory and the actual flow. And the actual flow, we also have wake, but the wake is much bigger, and we don't have this parallel structures, these layers anymore. These layers have separated, and it's very chaotic and looks like mixing. And in the end, a flow around a sphere can look like this, or like this, and it only depends on the state of the boundary layer. We will talk about the state of the boundary layer just in some minutes. But in the end, as you remember, I have two kinds of forces in the flow. I have inertial forces and viscous forces. Inertial forces can be represented by the product of density, velocity, and diameter, which is a characteristic length of a sphere. And the viscous forces can be represented by the viscosity. And basically, this ratio, it's called Reynolds number. I know that you may heard about it, and it's a formula used widely. And basically, the Reynolds number is nothing more or less than the ratio between inertial and viscous forces. And you can just imagine it like this. Viscous forces are damping or the viscosity is damping this inertial effects. And as long as this is under the specific ratio, around 2300 for example for a pipe, flow will more or less look like that. But once we are over this critical Reynolds number, we will have a flow field looking like here. And if we take a look at our ball, the diameter will not change. Density here as well, and viscosity will also, let's say, be constant for then it's only depending on the velocity. And so in the end, what we can say is that, let me take my marker, this is very important, velocity. And now let's try to understand why it is like it is. And therefore we have to take a deeper look at the boundary layer. First of all, let's start. I mentioned viscosity right now, which is also in our Reynolds number equation. What is viscosity again? Viscosity, as I said, is the resistance to deformation under shear stress. So let's say if we have here a wall, and here we have, let's say, a plate which is moving, then we will have a profile like this. So the change of velocity in y direction. And in the end, our equation is like this. So the shear stress is a gradient, the velocity gradient multiplied with the viscosity. And this viscosity is constant for Newton fluids like air. And now let's take a look at the boundary layer. Basically it was described first time by the very famous German researcher Ludwig Prandtl. And he said that the boundary layer is the area of flow next to the surface where viscosity dominates. And it's limited somehow. So we have, if you take a look at for example, this image where you can see the boundary layer, there we have an edge of the boundary layer. And this edge, in the end, it's artificial. It was introduced also by Prandtl, and a criteria which is used widely is the 99% criteria, which says everywhere where the flow velocity is under 99% of the free stream velocity, it's a boundary layer. And at the surface we have snow slip conditions, so the velocity is 0 as you can see in this image, and then the velocity is growing to the free stream velocity. And now it's very important to understand two things. First thing is more or less related to the left image. First of all, we have to realize that turbulent boundary layer can be laminar or turbulent or in between. I can remember in the first session we had some questions regarding turbulence, and some people were mixing up let's say laminar and turbulent because it's used a lot of time to describe like the overall flow, which can be laminar turbulent. You can have laminar turbulent wake, but you can also use it to talk about boundary layer. And in the end, boundary layer is laminar, turbulent, or in between in a transition. And if we take a look here, we can see normalized velocity profiles for laminar and turbulent flow. And as you can see, so on the x-axis we have the normalized velocity, and on the y-axis we have the normalized position. So this is basically what I showed you a little bit like here. And here you can see that the turbulent, for turbulent boundary layer, has a stepper velocity profile, much stepper. And this means two things. First of all, we have higher skin fraction, so higher skin fraction drag, because of the higher normalized velocity. The other effect is the separation, flow separation, will occur much later on the curved surface for turbulent flow. And the reason is that the turbulent boundary layer, it's chaotic, fluctuating, and therefore it has more energy because it's mixing with a fast-moving flow outside the boundary layer. And in the end, if you now take a look at the image on the right, when does the separation occur? The separation occurs when the adversive pressure gradient caused by the curved surface of the rear side of the ball, which you can see here, pushes the flow back and slows it down. You can see it here. So this is our velocity profile. Let me use my laser pointer. So this is our velocity profile. Flow is coming from here. And here you can see it, and this velocity profile is changing with the time. And what is happening if you take a look? First of all, the profile becomes more step. And the second thing which has happened, that if you take a look at what is happening also, is that here in the near to the wall, the velocity is slowing down. And then we have a point where it's like changing, we have a backflow. And that is exactly the same thing we talked about during the first session. At some point, the kinetic energy of the boundary layer is not big enough to act against the pressure gradient. And once it can't follow anymore the surface, it will separate. You will have a reverse flow causing an eddy. And this is what we know as a flow separation. And it's very important to understand that when you have turbulent flow, you have a thicker velocity profile, and therefore it will later separate. And this is really a fundamental thing. I see that you already wrote some questions, and with me today again is my colleague Akram, who will answer some of these questions during the course of this presentation. All the questions which stay unanswered, we will talk about them at the end, just to let you know. Okay, and I mean now I think you got an understatement for the influence of boundary layer, and now let's take a look on practical things. Here on this slide you can see left a diagram showing the drag coefficient, so the dimensionless drag of the sphere versus the Reynolds number. And since we are not changing, we assume the diameter of the ball is not changing, this can be also replaced by velocity. And first of all, because a lot of people asked me last time, why are we using drag coefficient instead of drag? The reason is, if we would use drag, we would not get this characteristic curve, because the overall drag, the total drag for sure, is increasing all the time. But if you, let's say, this term is not physical, but if you would take a look at the relative change of drag, you will use the drag coefficient, because then you consider also the change of inlet velocity, and it's something like let's say the relative drag for the flow state, and this will change difference. And let's take a look now on this graph. So here we can see how the drag coefficient is changing with the changing Reynolds number, and first of all it's increasing till a point, then it's dropping suddenly, and then again increasing. And here we can basically see all three states of a boundary layer. The first state is a laminar state, which starts somewhere very far left and goes till here, around 1/10⁵. Then we have this critical point where we have the transition. At this point, the boundary layer will start to become turbulent. So here, until we are on this part of the curve, the whole boundary layer is laminar. Here we get a transition somewhere that becomes turbulent, and from here the means if we go more in right direction, we somewhere come to the full turbulent boundary layer, where the full boundary layer is completely turbulent. And yes, as you can see, the pressure is dropping. And First of all, that sounds strange because when you remember the first slide, you saw that the drag was higher. And now again, it's very important to understand these two components of drag. For a laminar state, here, the viscous drag or the skin fraction is way lower. But the pressure-induced drag, because of the flow separation, which is sucking back the ball, is much higher. And it's changing here. Here, if we go to this transcritical state of the flow, so turbulent flow, we have a higher skin friction, but a much lower pressure drag because of the reduced separation bubble. And this image is showing it, I think, very clear. Here you see a laminar separation, which is much larger and occurring much more in advance. So it's separating basically, I would say, after 50% of the chord length. And with a turbulent flow, the wake structure is much more chaotic, but it's separating at a later point, separating, I would say, after 70% of the chord length. And just to underlie this argument, here you can also see the surface flow. So here this is from wind tunnel measurement, and here it was visualized using oil on the surface. So the error is coming again from the right, and you can see here we have very early the flow separation starting, which you can see here because basically here the wall shear stress is changing its direction. And here it's much later. And you can see the difference, especially that here we have this let's say, curly structure, while this structure is looking more or less, I would say, noisy. And here you can see this is a turbulent boundary layer, this is a laminar boundary layer. Now I would like to take with you a look at this video. You might know it. It's the famous Roberto Carlos, who is just shooting a goal. And what I like about this video very much, if you take a look, the trajectory of the ball is changing completely. First of all, it's flying in the right direction, and then it seems to change suddenly its flight direction and goes again to the left side. And basically the effect, which is the reason for this behavior of the ball, is known for a long time, but you can really see that nobody was expecting such a flight path, even not the cameraman, which completely lost the ball. And this banana kick, how it's called, is very interesting because you can explain it with some really fundamental physics. So what is happening here? Let's take a look. The reason for this strange flight behavior of the ball is the so-called Magnus Effect. And basically the Magnus Effect is the effect in which a spinning ball curves away from its principal flight path. Just imagine we have a ball, we add a spin, it's rotating, and then we have two possibilities. We can have topspin, which means the surface of the ball is moving forward with the spin. So if we're flying in this direction, this would be topspin, and backspin is the other way around. And basically there are a lot of different approaches to explain this effect. And it's like a lot of times in science, there is not one approach explaining it 100% perfectly, but let me try first of all with a very simple intuitive explanation to understand it. Basically, you can get an intuitive understanding from Newton's third law, because the flow is deflecting, or the body is deflecting the flow with a deflecting force, and from Newton's third law, it also means that the flow is deflecting the same way the ball. But basically what is happening here? Just imagine this ball is rotating. Flow is coming from the left. And let's make a very easy case. Let's say the flow here is rotating with the same speed here like the free flow velocity. So at this point, and let me take again my pen, maybe another color, green is not the best idea. So here they will add, but here they will subtract. And the result is that you have a, in the end, in the direction of the rotation, you have a higher, let's say, effective velocity, and here you have a lower effective velocity. And therefore you will have a higher pressure drop here, because from Bernoulli's law, which we I think also talked about, pressure drops with when you accelerate the flow, and therefore you will have a pressure difference which will result in an acting side force in this direction. And this effect is the reason why banana flip can work. So in the end, if you want to perform a banana kick, you have to kick the ball in a way that you add a rotational movement to the ball, which is superpositioning with the translateral movement of the ball. Right, and yes. Okay, so this was our short session about the fundamentals of football aerodynamics. And maybe this is a good point to answer some questions. So Patrick just mentioned that in reality the flow isn't behaving well. Yeah, that's true. Otherwise it would not be necessary to do CFD. Thomas has a question. Inviscid and viscous flow around the sphere at given properties of the surrounding air. Is there a dependency of the flow character depending on the diameter of the ball? 1 meter versus 1 micrometer? Thomas, this really depends, and basically the Reynolds number, or the is you can use it that way. If, let's say, 2 balls have the same Reynolds number, you will have exactly the same flow phenomena. So if everything is the same, but the diameter is different, it will be different also, different character. But if, let's say, for example, if we take a look at if the velocity is 2 times larger and the viscosity is also 2 times larger because we use a different fluid, we will get exactly the same flow characteristic. That's the good about the Reynolds number. It basically allows us to compare water flow around the sphere with the airflow around the sphere. And the Reynolds number is also the reason why we can use scale wind tunnel models, for example, in motorsports or car design, because later on you can compare the results still. Yes. Then there is a question by Pradeep. Is the gyroscope effect on ball? Honestly, Pradeep, I'm not very sure what you mean with gyroscope effect. I mean, from a mechanical point of view, if we're not taking a look at the fluid flow, but at the, let's say, mechanical behavior of the ball itself, I mean, in theory, there can be a gyroscope effect, but I think you can neglect it since it will be very, very small and only in the case that the ball is not perfectly rotating. A question by Mayuri, does the temperature play effect on the aerodynamics of ball? Yes and not. If you, sure, temperature plays a role, but you have to in the end you have to ask what kind of role it plays. For example, viscosity, and a lot of other material parameters are depending on the temperature. So if you have a different temperature, you have a different viscosity. But in the real world, I would say no. I don't think that there is a significant difference between, let's say, playing aerodynamics of a football if you play in winter or in summer. Then the next question is about the panel number effect of ball aerodynamics. This is something we're going to talk soon about during our live demo. But it's a very good question, Mayuri. Okay, guys, so I hope I answered your question related to the fundamentals, and I think we can move on, right? Okay, so let me continue. And right now we will do a live demo. And again, we have prepared something for you. So we will prepare a simulation of two different ball designs. The first ball is the generic ball design. Yes, and the second one is a very, let's say, modern ball design, which was, I think, introduced for the World Soccer Tournament in 2006. And what we're going to do today is two things. We will discuss about a parametric study where we took these different ball designs and investigated how they react on rotation, or how the aerodynamics around them react on rotation. So we took this ball and that ball and made a simulation series where we had a constant free stream velocity, and we varied the rotational speed from 0 to a given value for both ball designs. And this is what Mayuri was calling about this panel number effect of aerodynamic, because as you can see here, I mean it's both of the balls are a perfect square somehow, but still the structure of the surface is different. Here we have less but curved seams between the panels, or basically they're even not seams, they are flat. It's more like glued than stitched, while the generic ball has this other configuration of panels, and this ball is really stitched, so we really have a seam here. And just to maybe to draw it again, just to make sure you got it. Here it's more like this, and here it's like this. Great. Okay. And first of all, let's take a look at the results for the generic ball. And as you can see, here we only have, in all three cases, we have a free throw velocity of 22 meters per second. And here in the left, we have no rotation. In the middle, we have a rotation of 30 radians per second, and here we have nearly the double rotational speed. And what can we see? This is a slice through the velocity field, and so in both cases we are looking from top on the ball. So sorry. So this is the side, and what we can see basically is that we have a stagnation point here for sure in all the cases, and for the static simulation this stagnating point is exactly in the middle. And then we have here two dead water zones, which are result of flow separation, and we have this diverging structure of wake, which is splitting up here. So we have these two vortices which are creating the structure here. And when we start to add rotation, first of all we can see two things. The first thing is, I hope you can see it because it's quite small here maybe, that the stagnation point changed the structure a little bit, became thinner. And what is also happening, this is more important, the wake has disappeared. The wake structure changed. We don't have any more these two wake bubbles, but we have a very, very short wake bubble here. I hope you can see it's very, very small. And we have here the wake, this dead water zone, which is looking completely different. It's more stretched. And if we increase the rotational velocity more, we can see that this wake is becoming thinner and thinner. And basically the wake, these two separation bubbles are not disappearing. They are just becoming thinner and thinner, and that's the reason why it seems like the first one has disappeared here. And this is the Magnus effect that we can see here. The ball is rotating, and just to make sure you got it, it's rotating. The rotation axis is here, so it's going it's rotating like this. Let me just make sure that it's clear. So it's rotating like this. This one is from the show, not rotating. And this is the first very interesting thing. So this Magnus effect really has the effect on the overall wake structure of this ball. And if we, I mean, the velocity is not really helping us so much. We can use it to identify wake, but as you know, it's not the best criteria. And also, it shows like how the velocity distribution change, which makes sense, but it does not show what is happening so good inside the flow. So let's go to the next slide, and here we can see the so-called total pressure. And as you know from the first two sessions, the total pressure is representing the, let's say, first of all, the energy inside the flow. So, and red means, let's say, undisturbed flow, and everything like green, yellow, green, or blue means that we have lost energy, so we have vortices. And here we can really see what is happening. So you can really see very clearly this wake structure and how it changes and how it gets deflected more and more. And if we go a slice further, I think you can really see the effect of this panel. So here we have this generic ball, and here you can see that, for example, here you can see the first wake bubble, separation bubble, which is generated, and on the other one is here. We cannot see it right now because it's hidden by the position of the streamlines. And the streamlines are colored by velocity. So blue is a very low velocity, red is a very high velocity, and the surface of the ball is visualized or colorized by the so-called wall shear stress, which you talked about, right? And you can see like that here we have the flow separation, and if we compare it to the other ball, the structure is looking completely different. So we don't have this kind of flow separation here. We have another structure, and this is related to the path of the seams, because basically what you can see, the wall shear stress is increasing massively in the near and in this where it's stitched or seamed. And so this is generating, in the end, it's a reason why the flow is separating, and this different structure is much more optimized and results in later flow separation, which you can see here. Where it becomes blue, we have a flow separation, and here the blue area starts much later. Can see here, okay. But now let's take a look at the final results in the end. So this is a side force plot. And here we visualized like the results of this whole study. So you can see how the side force is changing. And since we have a constant inlet velocity, in the end the drag, the coefficient, will look quite similar. And what we can see here, that first of all, the drag of the standard ball design is nearly higher at any time compared to the new ball. And what we can also see is that we have a jump here, and here we can do two things. First of all, the overall drag is higher for the generic football because of the separations we have. So we have more separations in general and more drag because of the structure of the panels. But what we can also see is that here we have a jump for the new ball design, and here we have additional boundary layer separation. This separation is not directly related to the separation when we talked initially about the example, because here we have a rotational movement which is superposing the transversal movement. But here we have additional flow separation which we can take a look at. And therefore, let's now compare, for example, the two different ball designs. So here we have a constant rotational speed, and here we can see the total pressure. And you can really see that the separation bubble is much smaller for this new design compared to the old one. And if we take a look at the velocity, yes, it's basically the same effect. Yes, and finally, I would like to take a look with you on this vortex structure. So therefore, we have created a slide which is going through the ball in X direction and visualizing total pressure. So here you can see our actual position. We start just before the separation occurs. And then you can see how separation bubble is created. And this is very important. This Magnus effect will change the whole overall structure of the ball and of the wake of the ball. And here you can really see what is basically happening. We have this unsymmetrical wake. Okay, then I would like to present your homework today to you. So last week you had to investigate your angle study, or do your angle study for the race bicycle wheel. And this week the final homework is about investigating the effect of altitude for the Jambulani soccer ball, which was used for the 2010 World Tournament. And we will again provide you with a step-by-step tutorial as well as a handout project where you will find the geometry and everything you need. Yes, and yes, if you have questions, please use our forum. And if there are, now I'm very happy to, I'm very happy to discuss your questions with you, if there are some further questions. Okay, great. Seems like all questions were answered during the session. In the case you want to talk about something, just reach out to us using the forum. So thank you very much for being here. We thought it was a great journey with you. Hope to see you soon. Happy simulating and see you soon. Bye.